Statement I took is system responsiveness guard. Let us go through first problem understanding. By the problem statement, we understood that modern systems often become unresponsive due to high CPU usage and memory leaks, background process, or unexpected workloads spikes. Users usually notice the problem only after the system slows down or freezes. There is a need for a guard mechanism that proactively monitors responsiveness and reacts before failure occurs. Here, the note is by this the background process should not be killed but required to slow down and allow user to perform any other processes without freezing, hanging or etc. And now let us go through the objective of this problem statement. To maintain system responsiveness by dynamically slowing down resource heavy processes instead of terminating them, ensuring stability without data loss or interruption. Now, how the system slows programs down? We all don't know this very correctly. Now, let us go through it. CPU throttling, it reduces CPU priority of heavy processes, input and output rate limiting, and it slows down disk read or write speed. Now, third one is the memory pressure control, delay memory allocation requests, and fourth one is adaptive sleep injection, keeps foreguard apps responsive. Now let us go through the kernel level monitoring. Actually, this system is developed using the kernel operator. Now let us go through the monitoring. Why kernel level? Why is only kernel level used in this system? User space tools can observe performance but only the kernel can. Control CPU scheduling precisely. And the second one is it regulates input and output and memory fairly. And the third one is enforce throttling without trusting application. And it ensures that high accuracy, low latency reaction, no application modification. Now, the concept here is the kernel continuously monitors system responsiveness and dynamically adjusts scheduling parameter to slow down resource heavy processes while keeping the system interactive. And now let us know the kernel level architecture. Kernel monitoring module. It runs inside the kernel, hooks into scheduler, and the second one is collects real-time metrics, and the third one is minimal overhead. And now the responsiveness analyzer. It detects overhead conditions, and the second one is distinguishes foreguard versus background task, and the third one is it identifies non-critical resource hogs, and the third one here is throttling controller. Instead of killing processes, it lowers CPU scheduling priority, it limits CPU time slices, and the third one it delays input and output dispatch, and it also makes that it applies memory reclaim pressure. And the fourth one and last is feedback loop, measures impact of throttling, and the second one is gradually increases or decreases limits, and the third point is ensures smooth recovery. And now let us go to the step detection. The detection logic focuses on three key disruptive behaviors using simple explainable rule-based metrics derived from the OS scheduler data. And the first one is accuracy of detection. SRG achieves accuracy by relying on the direct scheduler observations rather than indirect or user space indicators. The key point here is a process is flagged only if its CPU behavior causes observable scheduling delays to other tasks. Second one is simplicity of detection logic. The detection mechanism is intentionally rule based, avoiding complex heuristics. And the third one is explainability. For each detected process, the system can clearly report that the CPU time used versus threshold. And the second one is number of preemptions cast. And the third one is measured delay to interactive task. And this ensures the detection logic it is easy to understand and easy to debug and easy to justify in real world and academic settings. And now let us go through the control mechanism. Once the detection module identifies disruptive processes, the SRG applies a control mechanism to protect system response. The mechanism is kernel assisted, non-destructive, and designed to balance responsiveness with fairness, making sure that no process should be killed unnecessarily. Kernel safety. All interventions occur inside the kernel scheduler or through the safe kernel hooks. And the implementation, scheduling priority, and CPU time slice limitation. And the second point is minimal intrusion. Avoid adding significant overhead interfering with normal OS operations. Use lightweight counters for CPU usage and preemption, and apply small incremental adjustments instead of drastic intervention. And the third one is robustness. Ensures the control mechanism it does not destabilize the system. Apply temporary and reversible adjustments. And here we have one table that is detected before and control action and kernel safety. We can see the differences happening in the three simultaneously in the step detection and control mechanism and kernel safety. And here when detected behavior, the first point is CPU intensive burst, and the control action makes that it temporarily reduce priority, and the kernel safety schedules safe priority adjustment. And when in detection behavior preemption pressure occurs, then control action is limit CPU time slice, and the kernel safety is it uses scheduler hooks reversible. And the detection behavior when it is interactive delay, the control action is boost interactive task priority, and the kernel safety makes that it preserves the fairness. And let us go through the system safety and stability now. But we forgot an example for the control mechanism. Let me tell the example. A detected process's priority is temporarily lowered so interactive task can run sooner without killing or forcibly suspended it. And now the system safety and stability. Ensuring system safety and stability is critical when implementing a kernel level mechanism like the system responsiveness guard, it is also known as SRG, is designed to maintain responsiveness without compromising OS integrity. The clear separation of the component is monitoring module collects CPU usage, preemptions counts, and waiting times. Detection module it applies rule-based logic to the identify disruptive processes, and the control module it adjusts priorities or CPU codes of disruptive processes. The reporting module logs disruptive behavior and intervention. And the second one is scalability reasoning. And SRG is designed to handle multiple processes and high system load efficiently. The metric collection, and it has detection logic, and it has control mechanism. The benefits with the system is it handles hundreds of processes, handles multi-core and multi-user environments, minimal overhead, ensures OS stability, and clean and architecture principles. The principles are kernel interface layer monitors scheduler and process metrics, and the decision layer implements the detection layer, and the control layer is a fully reversible, non-destructive, and the reporting logging layer is it provides explainable output, administrations, or user space tools. And finally, its demonstration quality before and after, and the impact. The impact here is improved system responsiveness, enhanced user experience, adaptive CPU scheduling, non-destructive resource management. And the conclusion of this idea is that the system freezing hanging will be sorted by using the kernel, which is a basic of OS, by priority scheduling, not by killing other process but reducing the priority. Thank you.